Hello and welcome to this video. In this video we're going to investigate the simple harmonic motion properties in terms of what they graphically look like. So we said in a previous video that we can define simple harmonic motion as the equation that the acceleration is equal to minus omega squared x. Now I'm going to put this in a box here because I'm going to prove that this is true no matter what case of simple harmonic motion we're going to have. But for this specific video, I'm going to take the case of a pendulum again because I think it is the most intuitive to think about. And what we're going to do is we're going to say what happens to the displacement as time goes on, what happens to the velocity as time goes on, and what happens to the acceleration as time goes on. And we're going to try and match up these graphs so that we can understand how everything happens at each point in a single oscillation. Okay, now if we want to get something to oscillate, we're going to first define the correct side. So we're going to have to say this is the point where I'm going to hang the string from, and this is my zero line. So this is my line where x equals 0. So I have 0 displacement. This is my what we call the equilibrium point. And let's say this side is the positive side, and that makes this side the negative side. And I'm going to displace it here by some positive amplitude A. Okay, so this is just the amplitude of this oscillation, so how far away from the equilibrium line it goes. So this distance here is A. Okay, now what we need to say is that this means initially at time t equals 0 that x is A. So that's a maximum amplitude here. So when t is equal to 0, x is equal to A. So we start at the top here. Then over time, we know that this is going to follow a path that's going to get closer and closer to this equilibrium point. So after some time has passed, it's going to become 0. But this isn't a linear motion. If anything, this is more of a circular motion, which means that we're following a partially circular path here. So we're never going to get a straight line that's going to take it from A to 0. It's actually going to be more of a curved path because the measure of acceleration that we get is going to change depending on how far this is, since we know the acceleration is basically pulling down due to gravity, but this is at some sort of angle, so we need to actually see what is the component of this acceleration. And since the component is dependent on the angle compared to the horizontal, which would basically be this angle up here, that means that surely the position and the acceleration and the velocity will all change as the angle decreases. So we're actually going to get a curve that is going to take it down to 0 that looks something a bit like this. Okay. So now we're at this 0 point. The next thing we're going to get is it's going to swing up to the top. And I say top, but this is actually negative the amplitude. And the same is going to happen. We're going to get a curved path, and I'm getting to negative A here. So I'm going to have a curved path that's going to take me down to here. I can probably do that a little bit better. It's going to take me down to here. Now that I'm at this point, when I reach my maximum, I'm then going to start to move back into the positive direction. So the next position I'm going to get to is back to this 0 point. So I'm going to go back up to 0, and then to complete one oscillation I have to get back to the same place. So I'm heading back up here to get back to A. Now what you can notice basically immediately from this is a cos graph. Okay, so it means we have some function of the displacement that can be represented by a cos graph, and how that's actually represented is an equation in your formula sheet that shows that x, the displacement, must be equal to cos. Now we're not going to say cos of theta here because axis here is not an angle, it's actually time. But the time that this takes is actually affected by the angular frequency. So we're going to say this is omega t. Okay, this is another way of thinking about this is mathematically, you can't put anything inside a function. So cos is a function. You can't place anything inside here that has a unit. so it has to be dimensionless, which means it can't be a measurement of time. Omega, we've said, is 2 pi over t, so we have to multiply it by time to cancel out seconds on the top and bottom. So we end up with a dimensionless constant. However, at this point that we have this, you'll notice I've left a gap here. That's because if we just have a cos function, the maximum amplitude we could ever reach is 1. So we have to multiply that by the actual amplitude. And this gives us our expression for the simple harmonic displacement. So this is the displacement when you're undergoing simple harmonic motion. Now we're going to apply something that shows that there's a similarity between these displacement time graphs and the displacement time graphs we had for linear motion, projectile motion. They're all the same, because we said for linear motion, the gradient of a displacement time graph is going to give you your velocity. So I'm just going to take the gradient at each point, and I'm going to plot that here on the velocity graph, and then we should see another form. So at the top here, so when it first starts, we can think about this as the gradient of this is 0. So we're going to start with the velocity as 0. But you could also think about it as, if I get rid of all these annotations and stuff, and we'll start back at the beginning, get rid of all this. As we start here at the maximum amplitude, when I first let go, it's not moving, right? So its velocity is 0 at the start. Then we can take the gradient here and find that actually in this whole thing, this is going to be a maximum, but this is a negative gradient. So we're going to go down here to being, I'm going to try and line this up. So this is going to be about there. So we're going to go down here to being a negative maximum velocity when it reaches here, because we know here it's going to have the maximum velocity traveling in the negative direction. Then for a while it's still going to be traveling in the negative direction, but it's going to start slowing down as it reaches this point here. And we can see that at this point here, when we get to here, we have a gradient of 0. So when we're going to get to there, we need to get back to there. So we go back up. As we're at this point, we now have velocity of 0 again. We're going to start going down in the positive direction. So we're going to end up with a maximum displacement here. The same reason there's a maximum gradient along this point. So we've gone up to a maximum gradient at this time here. And then we're going to get back up to the start where we end up with 0 velocity. And those of you who are pretty good with maths will show that this is actually a negative sine graph. We've just taken a sine graph and we've just flipped it around the x-axis, or in this case the t-axis. Now, for those of you who are a little bit more mathsy, you might also be able to see that in order to get from the displacement time graph, when I'm calculating a gradient, I'm just differentiating this. Now, for those of you who are doing maths, and you'll learn how to differentiate cosine and sine functions, and even tan functions and the rest of them, you'll know that if I were to differentiate this function, I would actually end up with the velocity, which is just the differential. I'll put this over here. The velocity is just the differential of x against time, and I'll let you prove this for yourself that this is true, is actually equal to minus a omega sine omega t. Now, I'm not going to put this in a box because this is not something that you have to know, but you do have to know the general shape of this graph. Now, personally, I think if you're doing maths, I recommend you don't actually memorize these or anything like that. I recommend just realizing that if you can get an expression for the displacement from your formula sheet, as long as you can differentiate a sine or a cosine, you'll end up being able to derive these from first principles anyway. But there is something about this that we can actually end up using. In this case, we said that this whole x changes as a cos function, but actually the amplitude is just whatever number is in front of the cos function. And in this case, we have a number which is a times omega, which means actually the maximum possible velocity we can get is the amplitude times omega. And that one's going to be minus the amplitude times omega. So this tells us an equation that is on your formula sheet, that the maximum velocity, which we know happens when we're passing the 0 point is equal to the amplitude of the oscillation multiplied by the angular frequency that it is oscillating with. Okay, and now we get to the acceleration graph. So now we're saying that we're actually going to have, if I go back to the start again, I can basically just differentiate this and then get my answer, but to prove it more thoroughly, we'll do the same thing we did before. In the first instance, the gradient here is a negative maximum. So if I were to continue this line, for example, this gradient to begin with is a negative maximum out of all the gradients that we have on here. Let me just get rid of that line. So I'm starting with a negative maximum down here. Okay, so I have a negative maximum. And we know that because at this point here, this is when we're going to start accelerating initially with a maximum acceleration in the negative direction. Okay, so I start with a negative maximum, but we said as soon as I get to this point here, I've got no acceleration due to gravity anymore, at least no component of that moving horizontally, which means actually at this point my acceleration is 0. So I must have come up to this point here being an acceleration of 0, and I do that in this kind of curve. Then as soon as I start moving past here, so as soon as the motion takes me this way, the acceleration is now going to pull this pendulum ball or whatever's attached to the end of this string back down, and so actually I get an acceleration that's traveling in the positive direction, which means I'm going to end up slowly ending up at a maximum positive acceleration because I'm the highest I could possibly be. So I'm ending up with a maximum positive acceleration this way, and that happens at this point here, so I'm going up to there. Then I'm going to go back down to where my acceleration is 0, so I end up back down at this point here. And then finally I go back up to where I have that negative maxima, which was around that point there. So I'm going to end up with this kind of graph. Now, again, those who are mathsy amongst you will probably notice that this is just a negative cosine graph. So that means that A must be equal to negative something cos of omega t. Now, to find the maximum acceleration in both cases, I could do the differential of this. Now, the first time we took the differential, we take the minus sign out the front. When we differentiate negative sign, it just becomes negative cos, hence why I've got this negative sign still here. But I have to take out another omega, so I end up with minus a omega squared. And that means that the maximum acceleration, a max, is equal to a omega squared, which is another formula that you have on your formula sheet. Now, I said that I was going to prove that this statement about simple harmonic motion is true, and actually if you look at this formula for the displacement, let me get rid of all of this and let me prove it properly. If you look at the formula for the displacement, we're saying that x is equal to a cos omega t, and the acceleration, we're saying a is minus a omega squared cos omega t. So if I set these two equal to each other, a is literally, they have the minus sign and the omega squared that is different, but a cos omega t is the same in both of them. So it's the same as saying it's minus omega squared times by x, okay? Because I could just write this differently, and I could say this is minus omega squared a, and this whole thing is just this expression for x. So this has to be true. Now, I did take the example of a pendulum for this. You will find that you can do the exact same thing for a mass spring system, and I'll leave you to prove to yourself that that is true, but this is the general graphs that you will find for any simple harmonic motion. It doesn't have to be just a pendulum or just a mass spring system, although those are the two main examples that you will see. These aren't the only examples of simple harmonic motion that exist. Now, the next question you might be asking is, how do you actually use these equations? Well, this first equation here, we're just saying we can determine, as long as we know the amplitude that we first set this pendulum or mass spring system to start oscillating with, we can know the amplitude or the displacement, the position it's at any given time, as long as we know A and omega. Okay, so this one is fairly straightforward to use. Now, this one only actually gives you the maximum velocity. So we wouldn't actually, since you're not given this equation here, you wouldn't actually be able to use this to try and calculate the velocity at a certain point based on this t. But there is another equation in your formula sheet which does allow you to do that, and that is v is equal to plus or minus omega times the square root of a squared minus x squared, where omega is the angular velocity or the angular frequency, a squared is the amplitude squared, and x is the specific displacement. So it's not the same as the specific time in which the velocity is, but for a specific place along this negative sign graph, you can then find a corresponding velocity for that. So this is your general expression for how would you work out the velocity if you're given omega and a. You can, given the displacement along this curve, you can find what the velocity is at that point. You can find the displacement based on if you know the time. And then the final one is the acceleration. Again, you can't use this equation since it's not given to you, although it will work, but it tends to not be the mark scheme answer, so you probably want to avoid going there. And so if you just have this, we can actually work out the acceleration by linking it back to the actual definition of simple harmonic motion as it is. Since we're calculating here a velocity at a certain point x, we can calculate an acceleration at a certain point x by using the actual definition. So these equations that are in boxes on this page are all the equations for the general case of simple harmonic motion that are on your formula sheet, and these would hopefully allow you to answer almost any question that you have on simple harmonic motion at this point. Thank you for watching.